Today's lesson is over section 4.7, Newton's method. Now, this is very similar to what we talked about with linear approximation, except we're going to kind of do the same thing, but we're looking to approximate solutions to our equations, so where we're crossing the x-axis. So using our slope-intercept form, I will be able to manipulate using the tangent line, so that's where the f of x sub 1 comes in. So plugging that in, the derivative of the tangent line, so f prime of x sub 1. But here, now since I'm looking for when my y is 0, I can actually plug that in for that point. I don't know what the x value is, so that's why I have x sub 2. And so I can rewrite this so I can solve for x sub 2 to get x sub 2 is equal to x sub 1 minus f of x sub 1 divided by f prime of x sub 1. And so this is where I can actually use this iteration to help me get closely approximate to where that x-intercept is when it's not a integer or a terminating decimal in most cases. So let's go ahead and jump in. So example 1, I want to use the method to determine the solution to cosine of x is equal to x that lies in the interval between 0 and 2. So I'm just looking for one value here, and I want to approximate to 6 decimal places. So first thing is I need to have my function in a notation where I can set it equal to 0. So I'm going to subtract x over. That allows me to get negative x plus cosine of x, and that'll be representing my function. Then take the derivative of that so I know what the tangent line's slope would be at that point. So I get negative 1 plus sine of x. So it kind of fits into our notation where x sub n plus 1 is equal to x sub n minus the original function, so negative x sub n plus cosine of x sub n, divided by negative 1 plus sine of x sub n. Now, when you're doing this, you don't need to have the x sub n all the time, and so I kind of drop it after a certain point. That's just general notation. It just means I can keep doing this over and over again until I get to 6 decimal places. So looking at the graph in between 0 and 2 for this function, I found that it looked like 0.8 was probably a good place to start. You can literally start wherever you want. You could have started at 0.7. That might have been a good one. But generally you want to be somewhere in the ballpark, so it means less iterations for you. But so for the first one, x sub 1 is just 0.8, so nothing to really do there. Then looking at x sub 2, I use the 0.8 to subtract what my function is at 0.8 and what my derivative is at 0.8. And so taking those two divided by each other, taking away from 0.8, it allows me to get 0.73985333064. You're going to get very long decimals with these. And so then from there, now that's my new x sub n. So I use that in the next one. So notice how that value moved down to the next iteration of x sub 3. And so as you're going down and doing these iterations, to know when to stop, you're looking for the repeating pattern of the first 6 decimals or 8 decimals, however many they ask for. So here I'm able to get 0.739085 for that one. Okay. Example 2 here, doing the same thing. I want to know where the roots of this equation of x to the 4th equals 1 plus x. So here I move everything to one side to get x to the 4th minus x minus 1, so that's equal to 0. I'm able to take the derivative here. Now notice they don't give me an interval to look. So here, this is when graphically I need to plug this in, see where I'm at. And so I notice that there are 2 x-intercepts, one in between 1 and 2, and one in between negative 1 and 0. It doesn't matter which one you start with. You're going to need to find both since they're asking for all. So I get to do this process twice. And so I'm going to start with 1. And so I plug that into my function and my derivative. I get 1.33333 repeating, and then I continue to do this over and over again until I'm able to get the same idea. So 6 decimal places that repeat. So the first time that I see 6 decimal places that have the same values in the same positions, that means that I have accurately approximated this number for the root of the equation. Now after getting to the 6th iteration of this, I see that I've finally gotten to where the first 6 decimal places are repeating, and so my answer will be 1.220744 for this one. Then I'm going to try the next one, and it'll start with -1. Also, you don't have to start with whole numbers like I did for the first one. You could start with decimals. So now, as you can see, down to 7 decimal places here, I'm able to show that -0.724491 would be my answer. Okay, have fun.